Now, please, Yichao Lu, I'm very sorry if I mispronounced your name. Please tell us how you won the competition.
Thank you. Yeah. So, hello everyone. My name is Yichao, and I'll be talking about predicting research trends in artificial intelligence with gradient boosting decision trees and time-aware graph neural networks. This describes my solution to the Science4cast 2021 competition, where I introduced a gradient-boosted tree-based approach and a deep neural network-based approach. My final solution consists of an ensemble of two approaches, and it achieved the first place among all the participating teams. So I'm currently a senior machine learning research scientist at Layer 6 AI, working on computer vision and natural language processing. I have also been actively participating in various machine learning competitions in my spare time, because I think it is a great way to benchmark my machine learning skills against the others. I'll begin with a quick recap of the task. In this competition, we're given a dynamic semantic graph where each vertex represents an AI concept, and edges between vertices are drawn when two concepts are investigated together in a scientific paper. Each edge also has an associated timestamp, which records the date of publication of the scientific paper. Given a set of unconnected vertex pairs at some time t1, we are asked to predict which pairs of concepts are more likely to be investigated by scientists in 3 years. Essentially, the task in this competition can be regarded as link prediction on a dynamic graph. My dataset split strategy is to create the training set and the validation set that mimic the test set. This ensures a high correlation of performance of the model on the validation set and the test set. Specifically, the training set includes data between the end of 2011 and the end of 2014, while the validation set includes data between the end of 2014 and the end of 2017. For both the training set and the validation set, I sampled 10 million unconnected vertex pairs. Although a larger training set typically leads to better performance, there is a trade-off between performance and efficiency, since a larger training set also incurs heavier computational costs. I found that using 10 million unconnected vertex pairs results in a good balance between performance and efficiency. I noticed that the competition dataset is highly imbalanced. For example, between 2014 and 2017, only about 3 million new edges are formed out of over 2 billion unconnected vertex pairs. This means that we only have less than 0.2% of positive samples. To deal with the scarcity of positive samples, I include all positive samples when constructing the training set and the validation set. The negative samples are uniformly sampled from the remaining unconnected vertex pairs. I experimented with alternative sampling strategy for negative samples. For example, I tried sampling unconnected vertex pairs according to vertex degrees to include more hard negatives in the dataset, but did not see gains as expected. I have also experimented with a data augmentation approach, which exploits the order invariance of the task. Since the model should output the same link prediction score for a vertex pair, regardless of its order, I tried doubling the size of the training set by swapping the order of the vertices in each pair. I found that this data augmentation approach only brings about marginal gains in terms of performance at the cost of much longer training time. Now I will describe my feature engineering approach. Feature engineering plays an important role in the winning entries of various machine learning competitions. I conducted extensive feature engineering with the aim of capturing the centralities of the vertices, the proximity between vertex pairs, and their evolution over time. Most of the engineered features are normalized by applying the rank transformation, which replaces the features with their ranks or average ranks in case of ties. This is because for most features, the distribution is constantly changing over time, and we need a normalization procedure to adjust these features so that the features within different dataset splits are comparable. For example, on the right side of the slide, we can see that the number of neighbors for the vertices have significantly increased from 2014 to 2017. Rank transformation ensures that the features in the training set have the same distribution with the features in the validation set and the test set. which improves the generalization performance of the machine learning models. Now I'll go through the set of engineered features used by my models. The features are sorted by their feature importance scores, which are combined from a trained light GBM by computing the total gains of splits that use the features. Feature selection is also conducted based on light GBM because decision tree-based models like light GBM are invariant to monotonic transformations of features and can handle missing values without imputation, which greatly simplifies the feature selection process. And here are all the features with importance scores over 10 million. We can see that the features corresponding to the number of new neighbors of the vertices 1, 2, and 3 years prior are the most important ones. This is because these features are very strong indicators of the current research trends. In addition, the Jaccard index is also a very effective feature since it measures the proximity between the vertex pairs. We can also see that the PageRank score is more useful than the number of neighbors of the vertex, as it is a better metric of vertex centrality. It is also worth noticing that I use the ordinal encoding of the vertices U and V, despite the fact that they're essentially categorical features. A common practice to deal with categorical features in gradient-boosted trees is to one-hot encode the features. However, given the high cardinality of the vertices, I found that ordinal encoding results in the best performance. And then for features with importance between 100,000 and million, we have features such as the difference of the Jaccard indices at different years and the number of neighbors for the vertices at prior years, which mainly captures the evolution of the features over time. And finally, I have features such as the PageRank scores and the Jaccard indices in prior years, which also help with the model performance, but with much less importance. Now I will describe my first approach to the competition, which is based on gradient boosting decision trees. Gradient boosting decision trees use an ensemble of decision trees to predict the target label. There are many popular gradient boosted trees implementations, such as LightGBM, XGBoost, and CatBoost, and their main difference is the way that trees grow. For example, LightGBM grows trees leafwise, which tends to achieve lower loss than the more common level-wise algorithms. I use LightGBM because I found it achieves better performance than XGBoost and CatBoost in this competition. Here are a few key hyperparameter settings to the LightGBM. In order to prevent the model from overfitting, I first set relatively small num leaves and max depth so as to limit the growth of the trees. I have also set bagging fraction to 0.8 and feature fraction to 0.9, which tells LightGBM to randomly select 90% of the data and 80% of the features before training each tree. And now I will describe my second approach to the competition, which is based on time-aware graph neural networks. The intuition behind graph neural networks is that nodes are naturally defined by their neighbors and their connections. Therefore, graph neural networks follow a neighborhood aggregation scheme, where the representation vector of the node is computed by recursively aggregating and transforming representation vectors of its neighboring nodes. I used GraphSage as the basic building block of my graph neural networks. GraphSage performs inductive representation learning on large graphs, and it is especially useful for graphs that have rich node attribute information. Here is the high-level overview of my graph neural network approach. The input to the model is the semantic graph we have in this competition, and the input vertex features are the concatenation of the engineered vertex features and the randomly initialized trainable vertex embeddings. The vertex representations are then learned using a cascade of graph convolution blocks. The learned vertex representations for the vertex pair are concatenated with the engineered features and fed into a multi-layer perceptron, which outputs the final link prediction score. The engineered features are pre-processed before fed into the neural network by first filling all the missing values with 0 and then standardizing each feature through dividing the mean subtracted values by the standard deviations. I applied an exponential decay on the edge weights of the semantic network so as to encourage the graph neural network to pay more attention to more recently formed edges. This also improves the time awareness of the graph neural network since it can now recover the exact time that a particular edge is formed from the edge weight. The adjacency matrix with exponentially decayed weights is defined using the formula on the right side of the slide. This is a rather heuristically defined formula. My main intuition is that when we are at the end of 2017, the importance of an edge formed 3 years ago at the end of 2014 should have decayed to about 90% of its original value. And an edge formed at the beginning of the year 2000 should only have 50% of its original performance. And here is the validation performance of different models I have experimented with. We can see that the graph neural network is able to achieve slightly better performance, while light GBM is significantly more efficient. The blend, which is based on a weighted average of the link prediction scores from the light GBM and the graph neural network, is able to further boost the performance, although by a small margin. Here is the ablation study on graph neural network approach. We can observe that directly applying the simple MLP on top of the engineered features fails to achieve comparable performance with light GBM and the graph neural network. Equipping the MLP with a vertex embedding module improves its performance since it can now learn vertex representations in a data-driven manner. The vanilla graph neural network, which performs graph convolution operations over the binary adjacency matrix, has a significant performance advantage over the MLP, since it is able to learn vertex representations aggregated within a certain neighborhood region. The exponential decay adjacent matrix further improves the performance by enabling the model to learn time-aware vertex representations. I have also studied the impact of the number of graph convolution blocks on the performance of the graph neural network. Empirically, I found that the graph neural network achieves the best performance when the number of graph convolution blocks is set to 3. This may indicate that the neighborhood information within 3 hops is most useful in the semantic network of this competition. And here's the final leaderboard result. My solution achieved first place among all the participating teams with more than 1.3% of relative improvement over the second place team. Either the light GBM or the graph neural network alone should be enough to win the competition, and the blend just further boosted the performance. And finally, I will discuss a few possible avenues of further improvements. In my experiments, the graph neural network approach is only marginally outperforming the light GBM, and most of the performance comes from the engineered features. In domains like computer vision and natural language processing, we have seen that the features learned by deep neural networks are consistently and significantly outperforming handcrafted features. I therefore believe that my solution is still very far from reaching the limit of the performance in this dataset. And the most promising way to further improvement resides in designing a better neural network architecture for representation learning instead of manually designing more features. There is a great paper from the NVIDIA Rapids team also discussing the performance of deep neural networks versus feature engineering in machine learning competitions, which I have included in the references. And also when creating the training set, I only used samples from 2011 to 2014, which limits the number of positive samples in the training set and makes the model prone to suffer from overfitting. A possible way to obtain more positive samples in the training set is to vary the start and end dates when creating the training set. We can obtain a number of training sets with different start and end dates and combine them into a larger training set with more positive samples. This can potentially lead to further improvement to our solution, since the performance of machine learning models is largely dependent on the size of the training dataset. And in addition, as I have shown, using a weighted adjacency matrix can lead to better performance of the graph neural network. In my solution, the weights for the edges are defined using a handcrafted formula. An alternative approach is to learn the edge weights with deep neural networks. For example, we can employ the graph attention network to dynamically learn the edge weights through an attention mechanism. Given sufficient amount of training data, we typically find that handcrafted features are outperformed by the representations with deep neural networks. And furthermore, in my graph neural network approach, the embedding vectors for the vertices are fixed through time. This limits the capability of the vertex embedding module to capture the evolution of the vertex over time. There is a recent paper from Twitter Research which describes a time-dependent graph embedding approach. Incorporating that into the graph neural network has the potential of further improvements. And this concludes my talk. Thank you for listening. And I would like to invite you to take a look at my paper, where you can see additional results and download my code. Thank you.
Thank you very much. This was very enlightening. I have a lot of questions and also see in the chat already questions. Maybe I start quickly with one that that you mentioned in the very end. You said that you only use data from 2011 to 2017 for training. Did I
2014, yeah.
to 2014, okay. What happens if you add the previous years also? Did the results get worse?
So I haven't tried that during the competition because the limited time. So I expected to bring about gains, but I think a careful normalization is required to ensure that like the features from different timestamps are comparable.
Mm-hmm. Mm-hmm. Okay, so this is probably in a way related to your decay, of the edge weight. So you chose a very specific value, 0.10 to the minus 4 or 10 to the minus 5
Yeah.
as the exponent. Was this just chosen randomly, or did you do some hyperparameter tests?
Yeah, so if you can see this graph at the left side of the slide. So basically, as I have said, my intuition is that if we are at the end of 2017, and I just assume that maybe a paper from 3 years ago has like 90% of its relative importance, and a paper like written at the beginning of 2000 will only have 50% of its importance. And this like 1e minus 4 just fits this my intuition well. So it is very heuristically defined formula, and I haven't experimented with other.
I see.
Yeah.
I see. If you now to combine those two questions, if you would combine your, if you would add more values in the training, and you have the decay, then the effect would be only very small, right?
Yeah, it won't be effect because this decay is variable, so we can vary this T1. So
I see.
Yeah.
I see. Okay, so I see other question by Michael Kopp. Thank you for the great talk and solutions. Could you give a bit more details around the wall times you showed? So what computational settings, how many GPUs and CPUs did you use?
Oh, so basically, this light GBM is very efficient. So it's running a CPU with 10 cores. So and it takes 5 minutes. So I think it's an Intel 10900KF. So it's a pure CPU-based implementation. And for the GN, it's running a single RTX A6000. So it's a professional graphical card with very large GPU RAM. So this is good because I can fit very large batch size, and it turns out to be very helpful.
Okay. So A question that I had about your huge list of features. How did you come up with the list? Did you just try to assemble every possible thing that you can think of, or were they did you find this similar list in the literature, or how did you come up with this feature list?
Basically, it's the intuition is this. Basically, I would like to. There are two types of features. One is vertex features, and the other is pairwise features.
Mhm.
And the intuition here is that we would like some metrics to capture the centralities of the vertices and proximity between vertex pairs. And another important aspect is to capture their evolution over time. And when we bear these in mind, like these features are just very intuitive. And
Mhm.
honestly speaking, I didn't spend much time engineering these features because I started the competition very late. I think only like 10 days before the deadline. So
Oh,
these
wow.
features can definitely be like further improved. Yeah.
Hmm. Okay. Um, so that maybe brings me to a question that you mentioned a little bit in the very end.
Yeah.
Uh, you talked about the automated feature generations, and we had a few contributions that worked with automated feature engineering. But we were very, very surprised that they could not outperform the hand crafted features, as you also mentioned. Do you have any intuition why that is?
Yeah, so there's a paper that I have included in the reference, which is from the NVIDIA Rapid team. So they have very good insights about this problem. And from my perspective, I think this is so I think it's mainly because we still don't have sufficient data in this competition, even though it is already a 10 times larger semantic graph than any existing in the literature. So it's still mm, not large enough for the model to fully capture
Mhm.
the patterns that are very useful.
That is
And
what.
also, yeah, and I think another thing is I um, basically I think because my graph neural network approach is also a very naive approach,
Mhm.
just applying some weights on the adjacency matrix, and
Yes.
it's still not fully it is not by design capturing the evolution of the features over time. And if I were to do this computation further, I would try to maybe incorporate an LSTM module on top of the GN and to learn this time awareness. Yeah.
Mhm. Okay. It's very interesting that you mentioned that the data is still not enough. So if you would design for instance, next year's competition, let's say there's a science forecast 2022, and we want to encourage automated feature generation. Your suggestion would be to try 10 times larger amount of data, or
I doubt if it's possible because I guess we're already like including every possible papers. And a possible approach is that we can, if we can somehow include some textual features without leaking the like information. I know this is like very hard because if we review this like text information from the papers, then people will just Google like what paper they are.
yes.
But if we can somehow, maybe through like topic model or other approach, or maybe even just if like the organizers can just run a language model on top of the papers and then give us like the learned embeddings of these like papers.
Mhm.
I believe this will like hugely boost the performance.
I see. Okay. Okay. Interesting. Um, Here, one note. We didn't use all papers from the archive. We only used the subset of machine learning, which is, of course, large, but it's maybe only 12 or 13% of archive. So potentially next year, or someone else could set up a competition where every scientific field on archive is used with maybe 1 million concepts and 10
I
million
see.
papers. Yeah. Okay. So that was very, very interesting. So let's see. I think I asked all of my question, except maybe what is the ord you said ordinal encoding of vertices, if you could.
Oh yeah, so basically, for my features, so basically this U and V are just ordinal encoding. For example, if in the data set this U is like
Mhm,
1,000, I just give it to like GPM or like the graph neural network as 1,000. But essentially, these are like categorical features and they don't have like order within it.
mhm,
So a common approach is to one hot encode the feature. So just we have like 64,000 vertices and just we just one hot encode whichever like index it refers to. But the
mhm,
problem is that with the high cardinality of this 64,000 nodes, this will include this will introduce a very large number of features and very scarce. Very the scarcity is also a problem. So I just define it using the ordinal encoding. So like GBM is like doing a split on top of this like ordinal encoding, but surprisingly, it still works quite well.
mhm. Okay. Okay, interesting. I didn't think about that. Okay. Cool. So I think this was all of my question, all of the questions that I see in the chat. That was very, very interesting. Thanks a lot for your
Thank you.
insights, for your contribution, and congratulations again for winning.
Thank you. Thank you, everyone.
Bye, and keep in touch.